Thanks a lot. It's okay. For the invitation, I want to thank Henrique, Alejandro, all the organizers. Always a pleasure to be here. So what I would like to, it's okay? What I would like to discuss a little bit today is somehow the Bi-Hamiltonian structure of this classical integrable system, which is called Calogero-Moser. Calogero-Moser will be a rational Calogero-Moser. And in particular, I will try to introduce special coordinate, which are called sometimes spectral coordinate for these systems. Now, so this is a work that was joined with Gregorio Falqui. This work is part of a much bigger project, which is somehow this project of study separation of variables from the point of view of Bi-Hamiltonian geometry. Okay, probably I should just make a comment. So separation of variable is quite a classical topic, and in particular for an integrable system. So here we have n function on the symplectic manifold M, and this function are supposed to be an involution, and generically independent on M. So what does it mean to be this system to be separable? It means that we can find let's say n relations which relate pairs of conjugate, canonical conjugate variables. So these canonical variables for the symplectic form. So this is what is meant for the system here, for this integrable system to be separable. So we can find these relations separable in the coordinates, in the canonical coordinate xp. Okay, so how this definition, let's say, is related to classical separability of Hamilton-Jacobi equation. So if we have just a function m, a function h, so we can write the Hamilton-Jacobi equation for this function. And classically, we say that S, which is a function of x, and alpha, this alpha, all parameters, is a complete integral of this equation. When this condition here is verified. Okay, so it is not very difficult to prove that if these end conditions are given to you, it is possible, if phi1, phi-n are given, then where we can write pi as a function of xi and alpha, then we can find a complete integral for Hamilton-Jacobi. I should say that what classically is meant to be separable is the following, that this S can be written as SI of xi alpha. So when this condition is fulfilled, it is possible to somehow to find SI, simply just a simple integration of this pi.
One question, what is the condition on the phi? Because they would not be zero there.
Sorry?
What is the condition of this relation?
This condition, I'm sorry, is that so this condition here is somehow the analog of this condition there. Okay, so now, as I said, this is a classical, let's say, classical topic that has some modern point of view. In particular, the modern point of view, which is, well, there are at least two modern point of view. One is due to Benenti, Eisenhardt, well, Benenti, let's say, and the other one to Scliani. Let's say that the question, the main question here is, let's say, to give intrinsic condition on H1 HL such that we can find phi1, phi(n) with the condition of non-degeneracy. Okay, in these two approach to the separability, actually, this condition somehow can be given, but both precise additional structure. It's not just enough to start from a symplectic manifold and integrable system, but you need to give some more structure. So, for example, in the Scliani case, the additional structure is given by a representation, a lax representation with spectral parameter, and the existence of a R matrix Okay, so in a lot of cases, it is possible to find this structure. It is possible somehow to answer this question. And so it is possible in some sense to, let's say, go to this separation of variables for the integrable system. But there are systems like Calogero, which do not admit, well, at least it is not known, neither a lax representation with spectral parameter, nor a classical R matrix representation. So in this case, it is somehow not quite possible to go to this direction. For Benenti is in principle is a different kind of treat a different kind of problem, not a really integrable system. Yes.
When you say classical R matrix, you're just denying the existence of that.
Deny, yes. No, I don't deny. Yes. Yes, but let's say that is not really what. At least, well, we don't know the lax representation, spectral parameter. And well, Scliani, at least, the Scliani approach Okay. But anyway, so, okay, so let's put some quotation mark maybe. So to solve, let's say, the problem in the case of Calogero-Moser, we need to get some different kind of strategy. And the strategy is given by, so let's say, A and B, C, by the existence of a Bi-Hamiltonian structure on the phase space. So, okay, so what I will briefly discuss is what a Bi-Hamiltonian structure is, what a Bi-Hamiltonian manifold is. Then, let's say that in the program that was started in this contest by Franco Magni and collaborators. So there are a few points that are somehow important to touch. The first point is to find the right class of Bi-Hamiltonian manifold. Then to find the right class of coordinates which will play the role of separation variables. And let's say 3, somehow, let's say answer the question. So I will try to explain a little bit how to go from 1, 2, and 3. Then I will discuss a little bit what the Calogero-Moser system. And then I will explain how to define, how to find a Bi-Hamiltonian structure for the Calogero-Moser system. And finally, how to find the spectral coordinate for this Calogero-Moser system. So this is the plan. Okay, so okay, so what is a Bi-Hamiltonian structure? Bi-Hamiltonian structure is simply a pair of Poisson structure which are compatible in the sense that if you take the Schouten bracket of P0, P1, you get 0. Equivalently, you can somehow translate this condition on the Poisson tensor on a condition on the bracket. And this condition is just that this slightly exotic expression should be equal to 0 identically for each choice of f, I, j, and k. And of course, we will say that a Bi-Hamiltonian manifold is just a manifold with a Bi-Hamiltonian structure. Then, so what is the class of Bi-Hamiltonian manifold that we are going to study? So this right class. The class is the class where one of the two Poisson structure is indeed invertible. So the definition of what is called omega n manifold. So this is a symplectic manifold and n is an endomorphism of the tangent bundle such that the torsion of n is identically equal to 0. And 2, so if I write P0 as omega minus 1, then P1 defined as n composed P0 is a compatible with P0 Poisson Poisson structure. So a omega n manifold is just, let's say, a Bi-Hamiltonian manifold where one of the two Poisson structures is invertible, come from a symplectic structure.
What's the torsion?
Yes, I'm sorry. So what is this Tn? Tn of xy is the torsion of n. So it is an x and y minus n and x y y.
Nightingale's torsion.
Yes, absolutely. Yes, yes. Yes. So this Tn is a 9 years torsion. Okay. So what is this is what is the class of manifold that we are going to consider. Here, more in generally, it is good to make a comment why this Bi-Hamiltonian in general manifold are important in mechanics. Because if you define a Bi-Hamiltonian vector field as a vector field that is Hamiltonian with respect to two different Poisson structures, then what happens is that the two Hamiltonian, F and G, are just in involution with respect to the 0 bracket and with respect to the 1 bracket. Now, more generally, you can define what is called a Lennard-Magritte chain, a sequence of functions, Fi, which have this property. P0 of dfi plus 1 is equal to P1 dfi for each I. Now, it is slightly more complicated to prove that if you have function Fi that satisfies this condition, then if you take any two of these functions, they are in involution with respect to both brackets. So this means in particular okay, that if you have a Bi-Hamiltonian vector field, this Bi-Hamiltonian vector field is, in a sense, endowed with a rich supply of first integrals, which are at the same time in involution. Of course, this does not mean that the system is integrable, because you don't know if the integrals are generically independent. You don't know if they are enough. But it is a kind of way to go toward integrability. Okay? So this is why these structures are somewhat important in mechanics. Okay, so going back to omega n manifold, now I will somehow try to explain how to answer to the second point, to find the right set of coordinates. Okay. So here is a definition of Darboux-Dignois coordinates. Darboux-Dignois set of coordinates, xi, pi, is a set of coordinates that are canonical with respect to omega, and that, let's say, diagonalize n. Okay, so the condition on n implies that the multiplicity of each eigenvalues is even. Of course, because you can have lambda I equal to lambda j for I not equal to j. Okay, it is reasonable somehow to restrict ourselves to the, let's say, less degenerate case. So when the multiplicity of each eigenvalues is minimum, so it is equal to 2. So in this case, we will say the following, that omega n manifold is semi-simple if you can find for each m a neighborhood such that lambda is not equal to lambda j, and a regular at the point m if these eigenvalues are independent. Okay, so this is a kind of non-degeneracy condition. Okay, now, under this condition here, there is a theorem that was proven by Magri and Gelfand and Zakharevich, as far as I know, that tell you the following, that if you have omega n manifold that is regular semi-simple, then you can find Darboux-Dignois coordinates. Okay, so how does this work? Very quickly. So first of all, you define this ik equal to the trace of the power of n divided by to k. And then the torsion equal to 0 implies that the ik satisfies the Magri-Lerner relation. Okay, so this means in particular, for the theorem that I state without proving, that these functions here are in involution. Okay. After that, if you consider this relation here, so we know that k, ik, is equal to the trace of n to the k, that under our assumption of regularity and non-degeneracy is the same that the sum of the eigenvalues to the power k. So you can take this relation here, and you can take the differential of this relation, and then doing a little computation, in principle, you prove that the differential of the functions I, the differential of the function lambda, are related in this way. So this matrix here is the van der Moor matrix. So on the locus where we are working, determinant of V, well, determinant of V is equal to the product of the difference of the eigenvalues. And where we are working, the determinant is not equal to 0. This means that we can invert this relation. So in particular, we can write the lambda k equal to some function of the lambda dis. And then from this relation here, it's very easy to prove that, well, this relation plus the commutativity of the Poisson bracket here is very simple to prove that lambda I, lambda j, 0 is equal to 0, lambda I, lambda j, 1 is also equal to 0. Then using a similar argument, you can prove that n star of d lambda k is equal to lambda k, d lambda k, where n star is the adjoint of n. So at the end, starting from this data, so this regular semi-simple omega n manifold, we arrive to prove that the set of eigenvalues satisfies two properties. The first property is that they are in involution. The second property is that they satisfy this relation. So in particular, this means that the eigenvalues of n give us 1/2 of the coordinate that we are looking for. Okay, so how do we find the other, the missing coordinates? In principle, using an argument very similar to the argument that you used to prove the Darboux theorem, classical Darboux theorem, you can prove the theorem, which is again is due to Gelfand, Zakharevich, and Magri, that we can find mu1, mu(n) such that lambda 1, lambda n, mu1, mu(n) is a set of Darboux-Nunez coordinate. Of course, well, we can do this, but again, to find this result here, we need to use somehow something very similar to Darboux theorem, which is not very efficient if you want really to find the coordinates somehow. Then, somehow we need to find some different way to do this. The different way, so this is what I said. The different way is given. Okay, so I will come back to this eventually. By the following observation. So let's start again from omega n manifold. Let's suppose that all these regularity conditions are satisfied. And then let's write the minimal polynomial of n in this form. Then, if you use Newton identities that relate somehow the symmetric function of lambda with the coefficient of this polynomial, we can prove, and this Magri-Lehner identity, we can prove that in principle this coefficient of the lambda, delta lambda satisfies this condition. And then if you read this condition on the level of delta n, we arrive that to this formula, that the n star of d delta n lambda is equal to lambda d delta n lambda plus delta n lambda dc1. Okay, so for this reason here, so for what is possible to prove in the case of delta n, it is reasonable to give this definition. So we define phi of lambda, which is a function, which is a smooth function on M, which depends on a spectral parameter. We call this function Nunez function generator if we can find a form, a one form, which I denote by alpha phi lambda, such that, well, there is this condition of regularity of alpha phi at lambda I, but then there is this other condition which mimic, in the general case, what we saw for the minimal polynomial. So the role of the one form alpha is played by this dc1. So in particular, if we call n of m the set of Nunez generating function of m, delta n lambda is one of these functions. And it is possible to show that this space of Nunez generating functions, function generating, is an algebra which is invariant with respect to the vector field y. The vector field y is P0 trace of n. Okay, so here now we have this result. This result, in some sense, answers the question how to find the second set of coordinates without going to the Darboux theorem somehow. So if we can find a function in this n of m such that n star d phi I is equal to lambda I d phi I, where phi I is the evaluation of phi at the point lambda I, and if this condition is fulfilled, so we take the derivative with respect to y of this function, we evaluate this derivative at the point lambda I. If this is equal to 1 for each I, then the pairs of functions here, lambda I, mi I, are Darboux-Nunez function, where the mi I are given just taking phi, evaluating phi at lambda I for each I. Of course, before we have the problem to use the Darboux theorem, which is in general is not completely trivial, here we have the problem to find this function that fulfills this property. Okay, so this is what I wanted to say, modulo some little thing about this generalization of Darboux-Nunez function that maybe I will go back later, about somehow the problem of find the right class of Bi-Hamiltonian manifold that in principle should give us the right setting to do separability, and find the right coordinate class. Okay? So I will maybe make a comment about 3 later. Now, I want to go to the other part of this seminar, that is this rational Calogero-Moser system. So what is this system? So this is a system that is it is a classical Hamiltonian system where we have n particles on a line, and these particles interact with a potential which is proportional to the inverse square distance of the particles. The Hamiltonian of this system can be written in this way, and the phase space of the system is just the cotangent bundle of Rn with the standard symplectic structure. So we can think that on the line we have x1, x2, xn, and xi, well, x1 is less than x2, is less than Sn. And this means in particular that this particle cannot cross each other. So this particle will start to move, and then what we have here is just the phase space here is just, the configuration space is just Rn, and the phase space, of course, is the cotangent bundle of Rn, which is what I wrote there. So this system was introduced by Calogero, Francesco Calogero, actually not in the classical setting, but in the quantum setting. And he conjectured that the classical, somehow, degeneration, the classical case, should be completely integrable. This was shown to be true by Moser a few years later. And Moser used somehow 2 ingredients. First of all, he was able to write the equation of motion in Lux form. And then what he did was somehow use some very clever scattering theory argument to prove integrability. Then I think that 1 year later, more or less, somehow Oshanensky and Perelman proved that there was another kind of Lux representation, which is called a standard Lux representation. I will not make too many comments about that, because probably I won't use it. But anyway, so this is what I want to say when the system can be written in Lux form. So this means that you can find 2 matrices in general. Let's call this L and B. And the equation of motion, well, at least this equation here, is in principle equivalent to the equation of motion of the system, where in this case, this particular case, the 2 matrices, Lij and Bij, are, in the first case, the matrix that we have there, and the second matrix is the matrix that we have on the second line. So the first matrix, Lij, is, in this form, is an Hermitian matrix, and the second matrix here is a skew Hermitian matrix. So just to have an example, so this is L for 3 particles and B for 3 particles. So again, what Moser did was to find a way to write the equation of motion in this form. He wrote these matrices, and he proved that the equation of motion really admits this Lux representation. Okay, so this is what I call a standard Lux representation. So in this case, you have 2 equations. You have the first equation that we have also in the Moser case, and then this first equation is somehow supplemented by a second equation where x is diagonal. And this diagonal x here, physical, these x1, xn, are the position of the particles. Okay, then, so this was what happened in the first stage of this story. Then the breakthrough, in some sense, was the proof of Kashdan-Kosten and Sternberg that the integrability of the system could be given via Hamiltonian reduction. So here probably I should make a comment. So you should remember that the matrix L of Moser is Hermitian. So constant, well, Kashdan, Kosten, and Sternberg start from this space, from this vector space. So these are Hermitian and by L matrices. And then they consider the cotangent bundle of this with the standard symplectic form, which is in this case trace of dA dB. Okay, here they consider the adjoint action of the unitary group. They lift this action to an action here. Now here, of course, what happened is that T star Hn can be identified with two copies of Hn with Hn. Here, of course, I'm using the fact that Hn is a vector space, and then there is a trace form that lets you identify the dual. So here we have the action of Un, which take AB into GA, G minus 1, GB, G minus 1. Now this action, since it's cotangent lift, is Hamiltonian, so it has a momentum map. And this momentum map is very simple to compute. Take A and B into the commutator of A and B. Okay, now, of course, what they want to do here is want to recover, but they want to do two things. They want to recover dynamics, they want to recover the phase space. How do you recover dynamics here? Well, how to recover the phase space, first of all. Of course, you need to make a clever choice. You need to find an element here which will give you what you want to get. So at the end of the reduction, you should get R to N with the standard symplectic form. So the choice that they made was to select alpha equal to I, well, square root of minus 1, minus the identity plus the matrix n by n where you have only 1. So this is a translate of a rank equal to 1 matrix. So what they prove, what is very simple to prove, this alpha here is a regular values for this momentum map. So you can take me to minus 1 of alpha, and you can take the quotient by G alpha, where G alpha is stabilizer in UN of the element alpha. So this gadget here is symplectomorphic to R to N with standard symplectic form. Now, how to prove at least that you get a quotient that is R2N? Well, the idea is a posteriori, very simple. What they show, so here we have me2 minus 1 of alpha, and then here we have the G alpha orbits. So what they show is that in each orbit here, so if here you have the pair A and B, for example, in each orbit here, you can find just one pair of matrices of the type Lx. In each orbit, you take any element in the pre-image of me minus 1 of alpha. In each orbit of this element, you can find exactly a unique element of type Lx, where L is the matrix written by Moser, and X is the diagonal matrix. Okay, so this means in particular that here there is a section of the projection. Here you have the symplectic quotient. And so if you look at these two matrices here, these two matrices, somehow, you will see that depends on P1, Pn, x1, xn. Out of the diagonal, well, x is diagonal, and out of the diagonal of L, you have elements of the type minus square root of minus 1, divided by xi minus xj. So let's say that this section here is parameterized by x1, xn, p1, pn. So the quotient here is really something that can be identified with R2n. And if you take omega equal to the trace of the L dx, you will see that doing just a computation, this omega here is really the standard symplectic form of R2n. Okay, so this was more or less what they did. Of course, well, there are several points that I'm not touching, but well, the dynamics of the system was somehow reduced, was obtained, reducing the linear flow on the big cotangent space, on the big phase space. So on the big phase space, they show that there is a linear flow, and this linear flow, after Hamiltonian reduction, reduced to the Calogero-Moser system. In particular, if you take H1 equal to the trace of L, H2 equal to 1/2, the trace of L squared, where here you get the total momentum, and here you get the Hamiltonian of the Calogero-Moser system. Well, here there is G, probably I can avoid to put G. Okay, so this is what somehow they did. And now, what about the Bi-Hamiltonian structure? The Bi-Hamiltonian structure of the Calogero-Moser system was discovered about 1996 by Magri and a student of him, Tiziana Marsico. And let's say that the theorem that can be phrased, that they proved, can be phrased in the following way. So you can find this some open subset of R2n, where the L is diagonalizable with distinct eigenvalues, lambda I, where this distinct eigenvalues are functional independent, then the function ik, which is ik is the trace of lk divided by k, and jk is equal to the trace of x, lk minus 1. This function here form a system of coordinates, so they are generically independent. And then, on this open set, the bracket defined using this ik and jk, using this ik and jk via this relation, are a pair of compatible Poisson bracket. And this defines a Bi-Hamiltonian structure for the Calogero-Moser system, which means that the vector field, which is associated to this function here, is Bi-Hamiltonian. Is Hamiltonian with respect to the first bracket, and Hamiltonian with respect to the second bracket. Okay, so this was a theorem that was proven by Magri and Marsico, but this theorem, let's say, first of all, was a kind of computational result. They somehow proved this result just showing that this it was reasonable to do because it was true for n equal to 3, in principle. And then they, in some sense, they guess that should be true for each n. And in particular, the result that they proved was quite distant from the result that Kazhdan, Costa, and Temple proved. So what we did, then I will come back to the previous slides. What we did was somehow to put the Magri-Marsico structure in the Kazhdan, Constant, Sternberg setting. So we proved that this Bi-Hamiltonian structure can be really somehow obtained by reduction. So let me go back of 2 slides. So we asked, in some sense, what was the geometric origin of this Bi-Hamiltonian structure. So here there is, first of all, a general construction. So let's suppose that we have a manifold Q. And let's suppose that we have L, which is an endomorphic with as 0 torsion. Then, if we define omega L via this formula, so in some sense we are twisting by L the Liouville form. Then what happens is the following, that after define omega L equal to d theta L, then the 2 brackets that are defined here are somehow compatible. So this is a kind of general result, is a general result, and in principle give you a lot of examples of Bi-Hamiltonian structure on the cotangent bundle. So you start from an inverse tensor on the base, and then you lift this tensor to a tensor on the total space of the cotangent bundle. And you end up with these two brackets. This omega, big omega, is the standard symplectic form, and this omega L is the omega L that we find just using this procedure. Okay, so here, just to make the thing in coordinate again, it is a computation to show that in the Dalbout coordinate for the standard symplectic form of the cotangent bundle, we have that xi xj 1 is equal to 0, that pi xj is equal to lji, and pi pj is this more complicated expression that involves derivative of the tensor. What is good to observe here is that if we define again p0 equal to the inverse of omega, then this n, which is p1, p0 to minus 1, is an inyoin tensor again. So this n is what we get lifting, doing a cotangent lift of L to the total space of the cotangent bundle. Okay. Now, going to the theorem that we prove. Okay, so we choose as a base manifold GLN, n by n matrices, and we define on the base on Q this operator, this LA, which take B in AB. So what is possible to prove is that this operator here is a linear Ninois tensor. So it is an endomorphism of the tangent bundle of GLN, which at 0 torsion. And then we can apply the previous result to this tensor. If we do this, we get, well, the first, let's say, Poisson structure, which is the standard one, this P0, the Poisson structure which is associated to the canonical simplicity structure. And then we get the P1 that, let's say that in this setting, has this form. So this is an operator which takes pair of matrices in pair of matrices. And the dot means that, it means where you have to insert the matrix. So I want to say that, for example, P1 of xi eta is equal to 0 xi minus xi a b eta, where xi and eta are two matrices, n by n matrices. Okay, so this is how these two Poisson tensors look like. And n, it is possible to show that n has this form, and the dual of n has this other form. Of course, the other identification, we identify the dual of GLN with the trace form. Okay, now, okay, yeah, there is this comment here, maybe it's important, that this function here, trace of ak divided by k, are a linear chain, and in particular, the Hamiltonian vector fields xk in the point AB have this form, 0 ak minus 1. And the other comment here that maybe it is more interesting is that what is P1? P1 is this Poisson tensor here. This, well, it can be proved that this P1 is the linear Poisson structure defining the dual of GLN, Cartesian GLN, where on this GLN, Cartesian GLN, you put this Lie algebra structure, this bracket. So this is just semi-direct product. Okay. Okay, so what we prove was the following, that this very complicated Poisson bracket that are written in coordinates can be obtained just doing some sort of reduction like I've done Constant and Stenberg, starting from these two Poisson tensors. Okay, now, how much time do I have? Thanks. Okay, now, this is what I can say about the Bi-Hamiltonian structure, the Calogero-Moser system. Now, let's go somehow to use this Bi-Hamiltonian structure, which is in principle is one of these examples of omega n manifold. So we are exactly in the setting where we can start the process of separation of variable. So, okay, so what happened for the Calogero-Moser system? Now we want to find the Darboux coordinate for this system. Of course, there is this general recipe, but in this case, we can do something better in some sense. So, first of all, we always work on this condition of, let's say, maximal non-degeneracy. So, we just use an open subset of R to N where these eigenvalues of L give half of the Darboux-Ninois coordinate. Now, here probably I need to make a comment. Now, this L here is the Lax matrix. Before, you had this Ninois tensor. But if you look here, well, it's just the same. Let's say, let's look at N. So you see that N somehow is diagonal. And on the diagonal, you have the first entry of the pair. You have pair A and B. And on the diagonal, you have this first entry. So this element A is the element that after conjugation goes to the Lax matrix. Okay? So in some sense, let's say that the spectral property of N double the spectral property of L. So going back here, so I'm just now looking at this open set where this L give us the alpha the Darboux-Nunez coordinate. And now the problem is to find this Nunez function generator with all these properties, because I want to find the conjugate momenta. Okay, so first of all, let's write delta L now of lambda as the characteristic polynomial of L. Then we have this theorem that if define g of lambda as the determinant of x times lambda minus L check, where this lambda minus L check is the transpose of the cofactor matrix, then this function here is the Nunez function generator. Moreover, it is not too difficult to prove that if you do y again is P0 trace of L. So if you do y of g lambda is equal to 0. And then from this, you prove that y of g lambda divided by y g lambda is equal to 1. Now, after proving that g lambda is a Nunez function generator, if you remember, the space of the Nunez function generator is an algebra which is invariant with respect to y. So here we have g lambda that is Nunez function, y of g lambda that is again Nunez function generator, and then if you take a quotient, it will be still Nunez function generators. And then if you believe that this first property is true, the second property follows. But now this means that this g of lambda divided by yg of lambda is exactly one of these Nunez function generators that give us the second set of Darboux coordinates. So in particular, if we define mi equal to g lambda, where g lambda restricted to lambda equal to lambda y, this mi are the conjugate momenta to the spectral coordinate. Okay, so here there is this comment that in some sense I already did at the beginning, even though Volodia did not agree with me. So this, again, these spectral coordinates are very important in the theory of integrable system, in particular, not only in the theory of classical integrable system, but also in the theory of quantum integrable system. And in general, what you need to have to find this Darboux coordinate, you have this additional structure. So you need to have spectral curve. You need to have this R matrix. A spectral curve is just because you want to find the functions which are in involution. Then you need to find something that tells you that these functions are really in involution. So you need the R matrix. For Calogero-Moser system, this is not completely clear. And then this procedure here really give us what we were looking for. So via Bi-Hamiltonian geometry, we were able to find this set of Darboux coordinates that, in principle, should solve the problem of separation of variables. Okay. Okay, I think that probably I should stop. Okay, so I will stop then.